sometimes in smart speakers, and now in the meeting room. And sometimes we see it in the hearing aids, in stethoscopes, and other medical devices. We usually publish the work with related work, motivation, method, results. In the end, I will summarize the work with a callback of the connection with the prior art, and then also talk about the contribution of the work, and then also talk about the contribution of the work, and then that's the end. So, from audio content to acoustic sensing, here we see as a sound level meter for noise exposure. It shows decibel level and flags if it exceeds the safe exposure limits. And then here we have single channel hard sound recordings to support clinician to diagnose if there is any abnormality in your heart sound. And then we have speaker tracking in the meeting room. The system could decide where to point the camera or which microphone to prioritize for clearest audio. And then we have indoor sound source localization for location-based services. And then we have, in the last, dangerous heart sound detection with data-driven model. Nowadays, AI models can classify the signal as normal or abnormal and can even grade the severity of the condition. So these are the cool stuff that acoustic sensing can do. So from simple to complex examples. And these systems are all rely on the same chain, that the sound, the target, generate an acoustic signal that propagates and picks up by the microphones. And we do the signal processing. And the system will decide what kind of information are we going to infer from the result. However, in signal processing, people often focus on algorithm and models much more. And in practice, microphones perform physical measurements of sound, so the errors will occur along this chain. So a common question emerges. These applications look very different on the surface, but they are all using or rely on the same thing, that is measurement devices with microphones. So this raises a key question. What ultimately limits what we can do with acoustic sensing in real-world scenario? This is the prior art that I have connected to, that it's literally called a huge microphone array. On these colorful boxes, these are the microphone modules. This is what I guessed what they have done over the 3D room. And in each of these modules, they have 16 microphones. So in total, they are having 512 microphones. It's a very large, dense microphone arrays, which enables 816 pairs of the time difference of arrival direction finding in the end. However, the measurement setup took 4 years, and they are very carefully calibrated and did in a controlled test rooms. This is the great demonstration of what is possible if you can afford a huge array like that. And from the year 5, they have started to have the research result like high resolution localization and beamforming. But in reality, this is like, just imagine how much of the time and the cost it will take. So it is very inspiring, but also we can say it's very depressing, because in reality, most real systems look nothing like that. So from huge arrays to modest and noisy reality. In practice, there will be always requirement for fewer microphones allowed in the system, and the environment constrained geometries for microphone arrays. And there will be different instrumentation choices for the elements or sensors you're using. And also, there will be dynamic measurement conditions. So the question raises, how far can we get with small arrays and realistic conditions if we design the measurements carefully? Speaking of measurement, so what would be the first thing you would think about to get rid of if you want if you are the one that conducting the experiment? A lot of people might answer noise. Of course, signal-to-noise ratio is a very important aspect that to consider when conducting a measurement. But what if we could use the noise somehow? Traditional sensing often relies on emitting energy, such as radar, ultrasound, and LiDAR, and they can achieve localization tasks under the umbrella by emitting energy under the umbrella of environment sensing. So the question is, can we do it the other way around with acoustic, in acoustic field? So this is when the idea comes out, seeing without emitting sound. What if we could detect and localize silent target to investigate the feasibility of silent object localization, where we rely on what the environment already gave us for free, and that is ambient noise? So, grid-based fingerprinting. This is widely used among the examples that I gave earlier, like radar, ultrasound, and LiDAR. This is basically dividing a room into different grids, and then you tell either the region or the location the target is. And sometimes you can also do it in a bigger room and then restrict an area of interest. And then you divided them into grids. So my first project is localizing a silent person in a 9-grid empty room using acoustic fingerprinting. So, acoustic fingerprinting. These two waves, the first one seen as you have taken the measurement in position A, and the red one you taking the position B from the same microphone. And because they're having a spatial relation, so the wave will have a similarity, and that is what we call correlation. So we measured a grid of positions, ambient sound with the empty room first, what measurement limits or constrains the result of acoustic sensing when using a microphone array. So we're talking about microphone array, there are aspects to consider during the setup. And I would like to do a comparison in this project. So there is microphone geometry and also microphone directivity. Here you see as the omnidirectional microphone on the right. It picks up the sound equally from all directions, has a full frequency response, which is very good for the silent object because we want all the ambient informations. And then we have cardiodirectional microphone. Geometries, which is linear, rectangular, and circular. So for linear, and I reduced 8 by half. I used 4 of them. It didn't really form a circular. It's a quarter of circle, and this is why I call it arc array in the paper 2. So in paper 2, the method I'm using is direction of arrival. Here you see the I and J as 2 microphones, and by the trigonometry, you can tell where the sound source it is. So in order to increase the diversity of called weighting factor, and then to correct this. So the result of the comparison, and then to correct this. So the result of the comparison in paper 2 is cardioid microphone has a overall better performance. That 2 as cardioid microphone has a overall better performance than the for stationary workstations, then it might cause problems when we see it in small, low-power devices, because sometimes it becomes too heavy of a task to process the algorithm for little real-time devices. So you might experience when you're using drones or home assistants, they're gonna pause a few seconds before they respond to you. So this is the idea of paper 3. Wideband was lower cost, computational cost. So in this one, we have increased the microphone to 6. I increased the microphone number to 6 to form a real circular array. And then the whole process, this is the illustration of the uniform circular array board that I have used. The process step is we capture the sound with a microphone array and then apply the new focus. Microphones that it allow us to record heart sound digitally and analyze heart sound objectively, and also monitor patients without imaging or radiation. But from measurement perspective, I have a question. What to do with the noisy heart sound has been captured in the old time? Here you see as a pumping heart. So the human body is also a complex acoustic medium. When you go to a doctor, you most likely experience if he wanted to listen to your heart. To a doctor, you most likely experience if he wanted to listen to your heart. He is going to take the stethoscope and then put the sensor on you in different positions. And these S1 and S2 are the typical positions the cardiologists use, or the doctor trying to figure out or listening to your heart. And the heart sound propagates through tissue, bone, and skin, so we can see it has increased, isn't it? So what we did is to detect these two pumps where exactly they're happening, and then to zoom in with the beamforming by the prototype stethoscope with 4 channels. And the reason to do that is because the doctors are interested in listening to the sound happening in between, which is from systole and diastole, and the dangerous heart sound happening in between there. So by that we could zoom in, or let's say make it easier to diagnose any kind of conditions. And the result is from raw single channel input to the S1, S2 detection, beamformed array output. We have verified S1 and S2 detection for systole and diastole segmentation accuracy with the PhysLNet database, and also with the real recordings with the prototype devices on the co-authors. And the microphone increase signal sectional gain for the murmur condition is 63%, and for the healthy heart condition is 33%. So that raises a question about the measurement quality. What is the measurement quality? Measurement quality describes how well the recorded signal presents reality. It's mostly influenced by noise, distortion, reverberation, and sensor replacement and contact. However, we realized that algorithms in the system and model right now can only work with what is measured, which means It only can be trained on what has captured. And when we designed that prototype system, we realized that there were ideas of how to improve the system. And that is a very common part to making a product or designing a system. So you get improvement and you enhance it incrementally. When you have a system like this, where you have AI component that uses data that has been gathered for maybe a very long time, then the question is, can we still do these small improvements without spending those years again gather the new data? Because sometimes it might be very hard to gather the data, such as in this case, heart sound. Rare cases of the heart disease doesn't really occur in 1 or 2 years, and the chances to capture that and putting it into the data set is even lower. So in this project, we try to predict with how the new system perform with our current system and current data. So what I did is see the current system as the new system, so we know the ground truth of it, and then we degrading the current system and make it acting like the old system. And we want to see if we split the data set as we train on the old one and test it with the new one, can we still say something about the accuracy increase to the future system that we're about to upgrade to? So I put different level of the noise on the current system dataset for training with highest noise level, and test the set with the old data with the most level of the noise, and then we try to see if we could get a result when we have a test set without the noise that had been added. And the accuracy increase showed that one dimension CNN has a almost it shows the result that it has been almost trained as on the highest SNR data, and almost meet the ground truth, that is 0.78%, and this result is 73%. So we could tell the accuracy increase about that model. However, 2D CNN is much more robust, not that sensitive as the 1D CNN. And the increase of the performance accuracy increase is not that big and significant. So we are curious about sound, and this is why my thesis have 3 questions. How does the room respond? Where did sound come from? And what do body sound tells us? These questions overlap because they rely on the same cues. We're always dealing with propagation, and we extract spatial cues using multiple microphones. We use time differences, and we often lean on spectral or feature to form fingerprints. Underneath is what those cues actually run on. In practice, the microphone array and its geometry, heavy use of correlation, the constraints reality of noise, and sometimes the constraints of dataset for the data-driven models. And the contributions of the work, I have achieved pinpointing the source or target in the indoor localization applications. The feasibility verified with silent object. Measurement setup has been investigated with different microphone directionality and array geometry, the measurement setup. And then I reached a faster, simpler way in computational cost for the microprocessors, and also we can call it teaching AI to listen by increasing the SNR. It's like giving the AI a better ear. So, and also the data quality dilemma has been investigated, see if we can conquer that problem for the data-driven models with those data that is very difficult to gather. And then the callback of the connection to the big science. So the huge microphone array, see it as a root experiment. It's a proof that something can work if brute force is allowed. So it's like you just throw more microphones. If we throw, it answers the question that if we throw enough microphones at the acoustic inverse problem, does physics stop fighting us? So by the result of reverberation averages out, localization stabilizes, TDOA becomes reliable after these forces, 512 microphone. And then it proved that redundancy matters. The reverberation is not a magic, and geometry with coherent contained rooms. So my question is, how do we get similar